Hey, oh, how's it going? Good, 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 good. Welcome. Thank you so much for being. Yeah, I'm kind of the co-organizer for this event. Yeah, I'm you. Yeah,
You're you. Okay.
Yeah,
nice
yeah.
to meet you.
yeah. Junjie will make a presentation for you today. I think he will be maybe here soon. He say he will Junjie, the other co-organizer.
Okay.
Yeah, he will be here make the introduction for you.
Okay.
And maybe we want to have a test see
Sure, yeah.
everything goes well here.
Sounds good.
Yeah, wonderful. Did you prefer use your own computer?
Yeah, I can do that.
Wonderful, wonderful. So. Wonderful.
Okay.
Yeah.
All right.
And
Do we need to make you a co-host so that you can hear, or
Oh,
you have
yes.
already done that?
oh, can you share? Maybe you can share your
I
screen.
cannot share. Yeah.
Oh, maybe.
Oh yeah, I can share. Wait a second. No, wasn't
Okay.
able.
1 second. Or do you want to do that?
Yeah, it should work now. Can you share your screen now?
Yeah.
Wonderful, wonderful.
I need to find where my thing is.
Yeah.
Here.
Wonderful. Maybe now we just test see anyone can hear from us. Yeah.
Oh yeah.
Uh,
So how do I do that? I'm not sure how to use it in this. Oh,
yeah, we can just ask. Maybe.
yes. Can you hear us?
Yeah. Wonderful.
Okay, great.
Wonderful. Thanks.
Thanks.
Yeah. Then
Sure.
Junjie will leave you.
I will do the
Wonderful, wonderful. Yeah.
projector.
Should I? Yeah, connect now.
Let's try to see whether it's
Okay. So let me close this. Anything that may pop up? Okay, I think we're good. So I'm gonna do. Actually, I need to probably connect to the power as well.
let's just see. I think there's some sure. Yes, already. Yeah, it works. 1 second.
Yeah, no, I made No, I'm just saying I need to probably connect to charge.
Okay, yeah.
What is this? Oh, I don't want this. What is this? Anyway, can I do slideshow? Oh, perfect. Oh, this doesn't work. Oh. Okay, good.
And maybe we wait until 12 o'clock.
Ah, sure, yeah. No problem.
By the way, the seminar is recorded. Is that okay? Yeah. So what we'll do is that we are going to post that on YouTube. So I think if you go to Icon's website, there is actually an announcement page.
Yeah.
So after I post on YouTube, I'm actually going to update that the announcement. So you have the link to it. So if you want to show that on the slide or anything like that.
Okay, sounds good. Yeah, thanks.
Currently, your talk is very popular. A lot of people are showing up.
Mostly.
We have VJ there at the end.
Oh, okay. Yeah.
Probably we need a larger room.
Yeah. So, like, what's the typical audience like?
I think there are students, there are faculties, but there's a post on icon. Yeah, so it's post on icon mailing list. So I think all the icon faculty, most of their students, for example, I will encourage my students to register for this mailing list. So they are going to know all this information. They think it's interesting, they will show up.
Okay, nice. Yeah, looks good.
Well, I guess. Okay, maybe we can start. Good afternoon, everyone. Welcome. So for those who don't know me, my name is Junjie Ching. I am an assistant professor at Purdue ECE. I work on power systems and broadly energy and sustainable systems. Also transportation system potentially connect to the power system as well. On the methodology side, I'm sort of interested in decision making on the uncertainty, game theory, as well as learning-based control, especially thinking about European performance guarantee, theoretical performance guarantee for that. So today we have the honor to have Murat joining us today. So Murat, he is also an assistant professor at ECE. I think you joined the same year as me, so yeah, about 2 years ago. And before he joined Purdue, he was working in MIT, IBM Watson AI lab in IBM research for a couple of years. Murat's research interests include causal inference, machine learning, and information theory. So welcome, Murat. Thank you very much.
Thank you so much. Yeah, thank you for having me. Hi, everyone. So yes, my name is Murat Kocaoglu. I'm at the ECE here. So this talk will be about causal discovery and an application of it in root cause analysis. So I like to keep things interactive. So if you have any questions, if anything is not clear, please just feel free to raise your hand and I'll try to address that. Okay, so yeah, the first half of this talk is mostly going to be about background and sort of trying to understand what causality is, what's the framework that I will be using, and later on in the second half, I'm going to talk about actually three separate papers, right? And then we are going to move from there. Let's see how it goes. So the first is modeling probabilistic causation. When I say causality, what do you really understand from it, right? So first we need to start talking about the definitions, right? What does it mean for something to cause something else? So for this, let's walk through this example. Let's say I have two variables, X and Y, right? And let's say X represents the percentage of population in a specific country who has access to clean water, right? So who in that country has access to clean water? And let's say Y represents the child mortality numbers. Okay, how many children do we lose in that country per year? Now, let's say you have some data set like this that you see on the right-hand side. You can get such a data set from the UN website, by the way. And let's say we hypothesize that X causes Y, right? So what does that really mean? Let's try to understand that. So if X causes Y in this framework, for me, that would mean that Y can be written as a function of X and some other noise terms that I don't get to observe. Okay, so this noise term will be captured in E here, called exogenous noise. But that's still not telling me what is really going on, right? So that's still just an equation, and I don't know what that really means. So what I'll do is next ask the following question. Suppose I have a magic wand, right, that I can use and I can intervene. What that means is that I'll use my magic wand to do some good in the world, and I'll make sure that X equals 100. Okay, so what that means is I'm magically making sure everyone on Earth has access to clean water. Okay, so you don't get to ask the question of, oh, how can you even do that, right? That's not allowed. Suppose I could do that somehow, right? The question is, would you expect to see different numbers for Y? Meaning, would you expect to see perhaps less child mortality in that alternative universe? And, you know, if you know how the world works, probably we would expect to see lower numbers for Y, right? So if this happens, then we can say X causes Y, right? Because my action actually changed the distribution of the variable Y. Okay, so X is said to cause Y if intervening on X, right? So taking an action and intervening on X affects the distribution of Y. That's how we talk about probabilistic causation. So I'm going to be using causal graphs heavily. So what do they mean? Suppose you have a complicated system, right? You can measure different parts of the system, right? Different parameters, maybe you have different sensors. And these different variables can cause each other in complicated ways. So we use causal graphs to represent these pairwise collections of causal relationships, right? So in this graph, for example, x3 causes x4, x4 causes x5. So whenever you see an edge from x to y, you say that x causes y. I'm not talking about any sort of quantification here. This is just a qualitative statement, right? So that just means intervening on x3 is expected to change or may change distribution of x4. Okay. And when you put the graph like this, then you are essentially sort of assuming that each variable can be written, can be generated, and is generated as a function of its parents in the graph and some exogenous noise that I don't observe. Right? So for example, x4 is a function of x1, x2, x3. One assumption that we have to make here, at least for this talk, is that the noise terms are jointly independent. Okay. Now let's try to understand the effect of an intervention on this graph. Before we had two variables, now we have more variables. How does it affect the causal structure, or does it affect the causal structure? Again, I have the same magic wand. Let's say I intervene on x4, right? Now, as I just told you, x4 previously was being generated by its parent set, right? So x4 was a function of x1, x2, x3 with some exogenous noise. So that graph made sense. But now I'm intervening and forcing x4 to take the value of 1, let's say, right? Some number. Now, what did I do? I changed the way x4 is generated from its neighboring variables. It's no longer being generated by its parents x1, x2, x3, right? So the graph I used before does not make sense anymore. Right? So I need to be removing the incoming edges to the intervened variables. So this is the effect of an intervention on the underlying causal graph. Okay. More precisely, when you intervene and say x4 has to be 1, that means you replace the structural equation that generated x4 with x4 equals 1. Okay. And you can generalize this idea and you can say, oh, I will intervene, but not force it to be 1, but maybe force it to take the value of a fair coin flip. You can make it random, right? So then that's called a stochastic intervention. But the same reasoning holds. Your intervention uses an independent noise, so everything is independent from the parents, so you still have no edge. So this is the effect of an intervention on the causal structure. Okay, so now let's talk about causal discovery. Now, one thing I need to talk about is dependency models, very briefly. Suppose you have this causal structure, right? What can I read off from this qualitative mathematical object, just a directed acyclic graph, about how the variables interact with each other? We already talked about causation, right? But we can also talk about statistics. We can also talk about dependency. So if you look at this graph, you can read conditional independences that the generated variables have to obey. For example, here x1 and x2 has no relation to each other, right? And they are not connected through what's called an active deconnecting path. I'm going to come to that later, which means that x1, x2 has to be independent statistically. Okay. I'm gonna skip the rest 3 statements because I actually have a dedicated slide on the separation for this talk, so I'm gonna explain that more on that slide. Okay, but the takeaway is that you can reason about conditional independences and dependencies just from the graph structure, which is great. Now the question is, okay, so the technical term is that a causal directed acyclic graph is a Bayesian network for the induced probability distribution. If you know what a Bayes net is. Okay, so the idea of causal discovery is that can we use CI statements, the condition independence statements, to sort of infer something about the underlying causal graph, right? To learn about the directed edges. But as the saying goes, correlation is not causation, right? So what we know, all of us probably know, is that you cannot deduce causation just from the data, right? How does that statement fit into this mathematical framework? It means that you can only learn the causal edges that are persistent across all the Bayesian networks that fit to my data. Okay, so you can have different Bayesian networks, explain your independent statements, but the causal edges that are common to all of them, you can actually infer that from data. Okay, we are going to see examples. For example, suppose I have this data set. I have 5 columns: race, parents' income, SAT score, zip code, salary. And for example, suppose it's a true causal graph, right? You have this observational data. You don't know this graph. So the question is, can you recover this graph just by looking at the numbers here from the table? So that's the objective of causal discovery, observational causal discovery. Now I can run condition independence tests. What will I see when I run condition independence tests? I'll see that, what is I here? Income, I believe. So income is independent from parents' income, is independent from zip code given race. Okay. But when you condition also on the SAT score, they become dependent. Right? So that's how this separation works. Again, I didn't explain it yet fully, but you can read off these independent statements and you can learn some things that I'll come to it next. But let's see how I can do this in the first place. So now I'll talk about just 3 variable case because it's the key for understanding everything about causal observational causal discovery. Let's say X causes Y causes Z, right? Or X causes Y causes X and Y causes Z. Or these are the same graphs. So my bad, Z causes Y causes X. Okay, just imagine the other side of the line. Now, all 3 of these graphs induce the same collection of independent statements. They tell me that X and Z should be dependent because there is a connecting path, right? So if X causes Y and Y causes Z, then X causes Z, correct? So there should be a dependence. Similarly, you can argue there should be a dependence in these cases as well. So they're not independent. And the moment you condition on the middle node, you're actually shielding off the effect, right? So if you know something, if you know a common ancestor here, which is Z, right? You can shield off their effect and you are just left with independent noise that I talked about at the beginning. But if you have this graph, so this graph is very special. This is called a collider. You have 2 nodes that converge at a single node. Right? So now this induces the opposite independent statements. This tells me that I have 2 parents, X and Z. They were generated from independent noise by my assumption. So they have to be independent from each other. But conditioning on Y opens up a collider. So that's how the separation works. And then X and Y becomes dependent condition on Z. So the takeaway here is that getting rid of all the technicalities that I talked about, there is one spatial graph on 3 nodes that you can actually tell apart from the other structures. Okay, so this is important for causal discovery because the moment I see this combination of independent statements, I'll just say, oh, it has to be this graph. If I see these statements, I can't say anything. It can be any 3 of the graphs. But if I see these statements, X independent from Z, and they are dependent given Y, I know it has to be this graph. Okay. So this graph structure can be identified from observational data. So you can learn causation from correlation sometimes. More on this separation. This is the dedicated slide I was talking about. So here is how this separation works. If you have a collider, right? So collider is converging arrows here. Then that node blocks the path. So now I'm checking whether U and V are dependent or not. And I'm trying to understand if I can traverse through this path. So, right, so that's the separation statement I'm looking for. If you see a collider, unless the collider is conditioned on, that collider is closed. So it closes the path that you have. For anything that's not a collider, it's the opposite. So the X here does not block it unless you condition on it. Okay, so it takes a while to get used to this flip side, but here the red colored Y node blocks this path, so U and V has to be independent because there's no deconnecting path. What happens if I condition on Y? Now I open the collider by conditioning on it. So U and V became dependent given Y. So what happens if I condition on Z on top of conditioning on Y? So the question is U and V independent given Y and Z, or are they dependent given Y and Z? What do you think? Huh? I definitely know people who know the answer, but they shouldn't say. Any ideas based on what I said so far? So remember what I said is, if you have a node that's not a collider, and if you condition on it, you block that path. So what that means is that if I condition on Y, but also Z at the same time, now I'm actually opening the collider path, but I'm closing the other path, other nodes passage, right? So Z is now no longer open, so you cannot have dependence, so you have independence. Something technical, but to make this presentation complete, I have to say, you don't have to condition on the collider, you can also condition on descendant of a collider, and that will also open the collider path. Okay, just if you're interested in the separation full statements. Okay, going back to this graph, now what can I learn from these statements? So this looks very much like the example I parsed earlier with 3 nodes. This says 2 things are independent, but they become dependent given SAT, right? So then that tells me SAT has to be a collider because conditioning opens a path. And then zip code should be a, rate should be a non-collider, right? Because condition on it blocks whatever path existed. So from that, if you are more systematic than I'm telling you right now, just to be more pedantic, you can actually recover this graph structure. Okay. So you learned some of the edges. You can say more things. You can also learn this additional edge from some reasoning that there shouldn't be another colliders. So this partially directed graph represents an equivalence class of decks that are consistent with my data. So whatever Bayesian network is consistent with my given data, it has to have all these edges. The undirected edges are things that are variant, meaning they can point in either direction. Okay, so I cannot learn them unless I have experimental data. So I'm going to come to that. Okay, any questions for this first part of the talk? I don't know how I'm doing on time. I guess we are good. Yeah. Yes.
In terms of something you said so
yeah. If I just have the parents, I cannot determine what?
You can't determine
right. So I mean,
can you repeat this question so that
yeah, the question is specifically on, I mean, correct me if I'm not understanding, but I think the question is that in this case, I cannot determine if race is a parent or a child of these other things. Correct?
Can you go forward in the graph or what?
Oh, that's actually a very technical question in the sense. So the question is, when you propagate these edges, can you only go forward? Is that the question? Yes. So the reason I did that, I didn't explain it, but the reason I went forward is that I used this reasoning that when I checked all the independent statements and I ran my first phase of my algorithm, I learned all the unshielded colliders. So that means the following. So let's go back. Suppose I want to orient this edge, right? If I oriented it from salary to SAT score, I would introduce unshielded colliders. That is not correct because I should have learned it if it was there. So I cannot have extra unshielded colliders, which means it has to be going out. So this is one of the so-called Meek rules that we use to additionally orient certain things. You cannot use Meek rule. Okay, you cannot use Meek rule to go back in this graph, but there are other Meek rules. For example, you shouldn't have cycles. So if you have almost a cycle, now you know how to orient the other guy. Right? So there are such Meek rules that you can use. But that's a good point. You can typically go downward. Yes, I would say that. Any other questions? Okay. So we know that, again, going back to the same point, we know that we cannot learn causal structures, causality from observational data. That's why we run the so-called randomized control trials, right? So what's a randomized control trial? You have a new drug, you want to test whether it works or not, or you have a vaccine, you want to test whether it works or not. So you randomly assign to patients, right, without telling them if they are getting the placebo or not. So there's a reason you are not telling them, right? Of course, nobody would want placebo, first of all, but there's another reason that you are trying to sort of make a perfect intervention, right? And then to sort of tell apart the backdoor effects, the confounding effects. So we're going to talk about those now. Why do you need randomized controlled trials for causal discovery? Okay. So suppose you have this triangle graph, x3 causes x4 causes x5, but x3 also causes xy. So this is a specific structure in the sense that there is no condition independence you can see from this graph. Okay, so everything is dependent. No matter what you condition on, everything will be always dependent because of the edges. Which tells me, just using observational data, you cannot learn anything causal from the data generated from this graph. But what happens when I intervene? Let's understand it. So as we discussed, if I intervene on x4, I'm removing the incoming edge, right? That's the effect of my intervention. Now, what do you see? You see that an edge has gone missing, which means potentially there's an independent statement that appeared. Okay, I can use that. I can check if x3 and x4 are independent, and they are independent in this case after the intervention, which tells me what? If the edge has been dropped with my intervention on x4, what does it tell me about that edge? The key is that I know the effect of my intervention, right? What the effect of my intervention would be. So if the edge has been removed after my intervention, what can I say about x3? Was x3 a parent or child? Yes. Yes, a parent. And why? Yes, but how did I infer that from the fact that the edge went missing? So yes, x3 is a parent, right? But how could I infer it from the independent statement and the fact that I reached to that point by an intervention? So remember what we said, right? So if you intervene on a variable, you remove the incoming edges. So I remove only incoming edges, which means I remove connections to parents. So if an edge went missing, that node must have been a parent before my intervention, right? And anything that you are still connected to will be a child. So you can actually learn the neighbors of x4 after an intervention. Okay. Any questions? This is like a lot of stuff I'm covering very quickly. But I guess a little advertisement, if you want to learn these in more detail, I will give a course next fall on causality. So come join. Okay. Any other questions? Okay, so that's some basics. Now, more advanced stuff. Pearl has developed something called do calculus. Now, what is do calculus? This is a way to assign. Okay, let me parse the slides. So now, in some cases, you can actually estimate causal effect from just observational data and the causal graph. So what I mean by that, so far we only talked about qualitative causal effects, right? Qualitatively, is X causing Y without any numbers in the picture. But in general, when you do a randomized controlled trial, you want to understand how effective your vaccine actually is, right? What's the percentage of survival with the vaccine versus not, right? So that's called causal effect, the quantification part of it. And you cannot know this just from observational data in general. But sometimes you actually can. So that's the beauty of this framework that Pearl developed. If you have the causal structure somehow, right, maybe some experiments or something, and observational data, then sometimes you can estimate causal effect without any experiments. Now, do calculus rules are used and are sufficient, shown to be sufficient to convert any interventional query to an observational function of an observational distribution, if it's possible. So there's a sound and complete identification algorithm proposed by Spitzer and Pearl in 2008. Now, why are all these coming up in this talk? It will be clear soon. But let's first walk through the calculus examples, right? So this do operation is essentially the intervention I talked about, right? I had this magic wand. I was forcing the, x equals 100 in the first example. Same story. I will force x equals the realization lowercase x. So that's what do means here. The question is, can I estimate the distribution of z given that I intervene on x? That's the question. Now here the reasoning is as follows. For example, the question is this the same as conditional distribution? Probability of y as z given x. What would be the difference between conditioning and intervening? So that's one thing we need to understand. And here's the main difference. When you condition on a variable, let's say x, right? What does conditioning do? Conditioning creates dependencies. Conditioning changes the posterior distribution, if you heard what that means. So if I condition on x, I'm affecting z, but I'm also affecting u. So that's not a causal effect, right? So if I intervene, I only affect through outgoing edges. But if I condition, I affect through both outgoing edges, but also incoming edges. Which tells me, in general, conditioning and intervening are not the same things because of that. When are they the same things? They are the same things when these vector effects are not there. Right? So when the vector connecting paths are actually not open, are actually closed. So for example, here, x will affect the posterior distribution of u. That's correct. This is the latent variable, unobserved variable. U will affect the distribution of y. That's correct. Right? But will it affect the distribution of z? No, because it's a collider. You cannot traverse through a collider that's not conditioned. So the vector path here that goes through u and to y will not affect z. But the front door here that is going through outgoing edges will affect z as it will in the intervention. So we say if there is no active so-called vector path, paths that start with an incoming edge from the intervened variable to the target variable, which is true in this case, then conditioning and intervening are the same thing. So this is the specific check that you are going to do. You are going to remove the outgoing edges from x and look at this graph and check if they are deseparated in that graph. Then you can say z given to x is the same as z given x. Okay. So this is rule calculus number 2. For some reason, I'm starting with 2 here. Okay, so another question. When does an intervention have no effect? You intervene on a variable, but it doesn't change anything in the system, in the target variable. So if the only connections are through vector paths, intervention cannot affect through vector paths, only through frontal paths. But if your only connections are through vector paths, then intervention will not do anything, right? So I can check this by this graphical condition. And then just says x given to x has to be the same as p of x. Okay, a slightly more complicated example. I want to check whether I can compute probability of y given to z here, right? Now here, I first check, can I say there is no causal effect, right? So 2 things we learned so far, I'm going to try to apply them. There is clearly causal effect, so p of y given to z is not the same as p of y, right? Is there a vector effect? Or can I just say it's the same as condition? There is clearly vector effect that goes through x, through u, and to y. So I cannot say y given to z is the same as y given z. So do I give up? Does this mean I cannot identify it from data? There is a way to still solve this. So you can actually use x to block the vector effect and then average it out in a smart way. So roughly, right? So how would you prove that? If you want to write the explicit proof, this do z distribution is just a probability distribution. Okay, it's just in a different universe, but it's still a probability distribution. So I can apply the probability rules on it. So I can marginalize out the variable x, just like I marginalize out in the chain rule of probability. By some out x. Now I know that the first term actually obeys rule 2, so I can replace do z with conditioning on z. Okay, because I blocked the backdoor effects by conditioning on X already. And here, X given to Z is simply P of X because Z has no causal effect on X. So I applied two things I learned in the previous two slides to reason about this more complicated causal query. So what do I get at the end? I get that Y given to Z is the same as the summation of observational distribution. It's simply a function of observational distribution, so you don't need an experiment to reason about this causal effect. This is also the famous called backdoor adjustment. Okay, in this case, Z is the backdoor adjustment set. Okay, so I walked you through, I think, almost all of these things. So these are the rules of the size story is a little more other things here that I believe what we discussed. Okay, so let's come to the contributions. Well, how am I doing on time? Oh, very good. That means there were no questions. But okay. So learning from experimental data. So here's our problem set. Suppose I have observational data, but I also have some interventional data. This is collected a priori, so I'm not designing experiments. I'm just working with whatever I have. Okay. Now, my goal is to learn a causal graph when there are latent variables in the system. This makes the problem way more complicated than what we discussed at the beginning with no latents. But we'll try to learn as much as we can. Right? You cannot always learn everything, as we discussed. You cannot learn some causal edges, and with latents, it's even harder, meaning you will learn even less. But what is the most you can learn? That's the question. So for this, we are defining and trying to learn an interventional equivalence class of causal graphs, right? Which means that these causal graphs could have generated the collection of data sets that I'm seeing. Just like the Markov equivalence class I discussed at the beginning with no latents. Now you have 2 data sets or 3, 4 data sets. If a graph could generate all of these data sets, I'll say that's an equivalence class, that's in my equivalence class. So I cannot tell that apart from any other graph that does the same thing. But that's the final question. So this is the paper if you're interested. So the key idea that we leveraged here is that we realized we can use the do calculus rules as constraints that are put across interventional distributions. For example, if you say y given do x is the same as y given do x comma do z, right? If you observe this in the data, can you use this invariance to reverse engineer parts of the causal structure? And if yes, how? Systematically how? Right? So that's what we tried to do. And this sort of extends the condition evidence-based learning framework to the interventional setup with latent variables. I'll just briefly talk about different types of interventions, because here we are focusing on the so-called soft intervention, what the difference is. So if you have x causes y causes z, here I'm just going to write the conditional distributions, not the functions, not the structural equations. X is sampled from some distribution, y given x is sampled from p of y given x, and z given y is sampled from p of z given y. So this is just Markov chain. If you hard intervene on y, it means you are completely removing the incoming edges. You can completely destruct the causal relation between x and y. But this may not always be possible. Perhaps, let's say you're a doctor and you prescribe to your patient some drug, right? But the patient says, yeah, I'll get it, I'll take it, right? But they just don't, or they take every other day. So you cannot fully control the mechanism, but you can influence it a little bit. So that's called a soft intervention. So the causal relations are still there, but you perturb the mechanism a little bit. So the conditional distribution now became something else. It became PT. So that's a soft intervention. Okay, so I won't go into too much details of all the technicalities, but there's a way to extend Pearl's do calculus to soft interventions. Very similar story. So I'm not going to go into details of it. Our goal again is to use distributional invariances that we see in the data to infer graphical information about the causal structure. Now the do calculus rules have a specific structure But for example, on one side, you have XZ, a set, and on the other side, you have X, a subset of that set. But in general, you might have a distribution where you intervened on a set S1, and a distribution where you intervened on a set S2, and they're not subsets of each other. So you might have arbitrarily different interventional targets. That's the first challenge. How can we handle this case? So a little spoiler here. What I'm saying is that just like the separation, do calculus rules go in one direction. They say if you see this graph separation in the graph, that means they are independent, or that means this invariance holds, right? But we are going to go in the other direction. So that's what you do in causal discovery. You sort of assume this sort of faithfulness assumption that says, if you see some dependence or independence, that is indicative of the structure and not just coincidental due to numbers aligning. So we're going to use the same idea here, just to make that clear. So the first thing we did is to extend the calculus to these arbitrary sets, arbitrary subsets of interventions. You can write this rule, slightly more complicated, but uses the same ideas. Okay, and then we can use this to write sort of any Markov equivalence class of causal graphs. So I will say a tuple of distributions. And so now I have multiple distributions: observational, intervention 1, intervention 2, intervention 3. I will say a tuple of distributions. A tuple is I Markov, interventionally Markov equivalent to a graph, to a causal graph, which essentially means the causal graph could have generated all these distributions. Okay, I'll say that's the case if these invariances hold in the distribution. So when you see some graphical separation statement on the right-hand side after the if statement, if this implies the distributional invariance on the left, I will call that graph I Markov equivalent. The distribution tuple I Markov to that graph, and all such graphs as I Markov equivalent to each other. Okay, so this is what I was talking about. So again, these are the graphs you cannot tell apart from data itself. So one issue is that these are very complicated graph notations. I think we'll pass this whole thing. Right? It's not very intuitive on how to compactly represent all these statements. So for this, we are introducing the so-called, we are not introducing, to be honest. These are already introduced by Pearl in 1995 paper I took snapshot of in the proof. Okay, but we are also using them to represent interventions. So how do you do that? Suppose you have observational data, but also interventional data P sub X, right, where you intervened on X. I will represent both of these distributions with a single graph, where the F node points to X. Okay, so I will say if F is equal to 0, right, then this thing reduces to observational distribution. If F equals 1, it reduces to interventional distribution. So you can combine distributions like this. Now, one thing we can check is that, are the independent statements I read on this bigger graph with the F nodes, are they significant? Are they representative of anything? Right? If so, I can use this structure. Z here is graphically separated from Fx. If you parse the separation conditions, they are graphically separated. And this implies the following, that P sub X Z equals PZ. What does this mean? The subscript notation might be confusing. It's just do X. Right? This tells me do X has no causal effect on Z. So I can actually read off that invariance or capture that invariance across different distributions with this F node and the independence of the F node, graphical separation. What else can I read off? There are many things I can read off. I'm not going to parse this whole thing, but you can read conditional independences, and this tells you about do calculus rule 2. Conditioning is the same as intervening, right? Or so on and so forth. So this is a nice structure that captures the invariances across distributions. First used by Pearl to prove calculus, but this is not general enough for our needs, so we have to extend it. And again, I'm not going to go into details, but we came up with an equivalence relation of this invariance statement, with the graphical separation statement, with the separation statement including several F nodes. Okay, so skip that. Okay, good. So now let's see what we just did so far. You have this causal graph. you edit F node to represent your data set. You have observational and do X data sets. Now, there is something called ancestral graphs and maximal ancestral graphs, that actually are structures that capture the independent statements that you see when you have latent variables. Okay, I'll just leave it there. So the mag of this graph is all you can learn from data. Okay. So we are going to use that. And essentially our goal will be try to learn this structure from data. Okay. So the key here is that the separation statements in C, the augmented, the maximum ancestral graph of the augmented graph, they preserve the separation statements in B, which preserve the do constraints, do calculus constraints in A. Okay, that's why it's useful for our purposes. So we have this main theorem. This gives you a graphical characterization of when you can decide two DAGs are interventionally Markov equivalent. Okay, so you don't need to do very complicated things. Thanks to this theorem, you just need to go and check if they have the same scatter, they have the same unshielded colliders, and they have the same discriminating, they have the same colliders on discriminating paths. Again, that's a detail. I'm not going to go into that, but you only need these three conditions, and you can say these are interventionally Markov equivalent for our framework. Okay, so this gives a complete graphical characterization of I Markov equivalence between causal graphs with latent variables. Okay, so how do you learn this? Some invariances on that graph, augmented graph, are testable, some are not testable, some don't mean anything, but we are okay with that, right? So we'll just use the testable statements to learn the graph. And here's one algorithm. Again, I'm not going to go through it, but this can be simply seen as an extension of the famous FCI algorithm, which was used for learning ancestral graphs with latents just from observational data. So we're extending that to observational and several interventional data sets. Okay, so again, I think I should skip this. What if intervention targets are unknown? We have a follow-up paper on this, and it turns out you can do most of these things similarly, and you can actually, on top of that, learn intervention targets. You need to change the algorithm a little bit, but essentially most of the stuff that I talked to you about goes through without a problem. Okay. Any questions? Yes.
Always possible to use the efforts after both, or whether we can construct other than for the interventions that we have.
So the question is that when you have observation and intervention data, can you always use this F node to represent both, or does it depend on the graph structure or something else? Yes. So if you have two data sets, you can always use this. If you have more than two data sets, the way I'm not sure how much of the detail to go to, so I didn't go into details, but if you have more than two data sets, the way we handle this is you check every pair of data sets. So for every pair of data sets, you create a new F node that captures the relative difference. So from this data set to that, what has changed? It tries to capture that. Now, when you do that, technical problems arise. One technical problem is that you have multiple F nodes, but the independent statement between F nodes, they don't really mean anything. They don't correspond to anything real because these are made up nodes. Although I showed you with a single F node here, let's go back. I showed you that with a single F node, it's all fine. So any independent statement corresponds to a meaningful invariance, solutional invariance across data sets. But if you have multiple F nodes, that's not really true. So then technical problems arise. So that's what we had to address in this paper. But you can still, so that's what I'm trying to convey with this picture. Even those statements arise, F1 is independent from F2, right? That doesn't mean anything. That's not a testable statement, but I don't care. It doesn't affect my characterization. As long as I know what to check, when to check. Any other questions? Oops. Yes.
Is this mag augmented thing mostly useful for just characterizing? Is it like a simplification that makes the math and theory and possibly algorithm easier, or is it kind of fundamental in the sense that like without this you couldn't characterize it, or is it just super complicated to characterize it without it?
Yeah, very good question. So the question is this MAC stuff necessary, or if it's necessary, due to what? Is it a fundamental need, or is it like makes things simpler at some level, right? So it depends how you look at it. I would say it's a fundamental thing from the following perspective. It's fundamental in the sense that it tells you what can you learn at most using independent statements or invariant statements. It actually tells you these are the edges you can at most hope to learn from the data that you have, right? But also it's a compact representation of all those invariances. So in that sense, you can perhaps represent them like a list, right? But that would be exponential. So this is a very nice compact representation of all the invariances that you can see in your data in a single graph, even if you have multiple data sets. So I would lean towards more fundamental than technical. Any other questions? Okay, so now we have an application, less theory, but algorithm. Now, given these results, right, we would like to understand if we can use this for a specific application called the root cause analysis. So root cause analysis is that you have a system that you're operating, right, maybe a server or something, and then something broke down. You don't know what broke down. You want to understand what went wrong. Which service was the cause, real breaking down service versus that affects other things. So now you see a bunch of things failing, right? So more precisely, you have a system, right? And then this system is complicated. It's a very big system. You have, let's say, hundreds of services in it, or microservices in it, which is what we are focusing on. Then something failed. You want to understand what failed. So today in industry, an average expert spends around 3-4 hours, not an average, actually, a team of experts spend 3-4 hours to debug a software failure. And there has been instances of things going bad in the past for certain companies, right? So our goal here is to automate this process of finding the root cause of a failure using these causal discovery ideas that I presented. Okay, so this is the paper, if you want to check it out for this problem. So here is the key idea. It's a very simple idea. Now you have normal operation for your system and you have abnormal operation for your system. Right? The key idea is to view the abnormal operation, anomalous data set, as a data set that's obtained with an intervention. Okay, so remember, you have a causal graph, you intervene that changes something. Since from normal operation to abnormal operation, something changed, can we see this as an intervention and try to identify the intervention targets just from the data, complete data-driven principle. Okay, so that's the goal here. Again, you can use an F-node to represent these two data sets, normal and abnormal data sets. And then our goal will be now to understand what the target of F-node is, which node F is pointing to, so that will tell me the root cause of the failure. How is it low battery? Oh, this is not charging. 1 second. Let's make sure this doesn't die. 10%. I can make it perhaps. Maybe we'll try this. This seems to be not working. I don't know if it's my laptop or charger. Should I keep going? Maybe try to finish it off? Okay. Okay. Okay, we have 8% charge. That's the limit. All right. So that's the main idea, right? Let's see how that idea might be useful. Again, I can use independencies that I see with the F node that I constructed. So F node will be very simply constructed as in the first data set, F is equal to 0. In the second, as F is equal to 1. Okay. So now if I see X independent from F, that means that in the normal and abnormal data sets, the distributions are the same. So intervention could not have been on X, right? The root cause, the failure could not have been X node. Similarly, I see that Z and F are independent given Y. In the data, I read the zone. Right? This tells me that the conditional distribution of Z given Y did not change from normal to abnormal data. Right? That tells me that intervention could not have been on Z. So Z could not be root cause. But I will see that the intervention actually affects the conditional distribution of Y given X, which tells me that intervention could have been on the variable Y. Yeah, so this is how you would reverse engineer from the data. But I don't know the graph. So although I explain as if I know the graph, there's a way to avoid knowing the graph as well. So you can do this completely data-driven. So what are our contributions in this paper after this idea? Full graph discovery may take a lot of time, which is not affordable for the specific application. You want to be as quick as possible to avoid the downtime, to keep the downtime low. But for us, we just need the root causes, not the full graph. So can we make the algorithm more efficient? So for this, we proposed a hierarchical root cause discovery algorithm. So essentially, you can divide your data set variables into smaller subsets, and then run causal discovery within them. This makes the algorithm very efficient. And then you can combine the root causes you identify in these subsets and then run it again and again, right, until you eventually stop. So this hierarchical idea makes a big difference in terms of runtime. This is the algorithm. Now, what's nice about it is that it's a sound algorithm, meaning that you will always identify the root cause correctly. You will never miss a root cause because of how the system works. But it might return false positive. So it might point to something that you think is the root cause, or the algorithm thinks is the root cause, but it's not really the root cause, right? So it's sound but not complete, but that's okay for this application. So if the root cause is one node and you point to 3 nodes, that still saves the engineers a lot of time to know where to look at. It's really narrowing down the space really nicely. So I should probably skip the results, but essentially we compared this with the existing methods for root cause analysis. The precision is really nice. There are different reasons here. So next slide is better, I think. So epsilon diagnosis here simply checks correlation test. So it's actually very fast. But then you can see we are checking not correlation, but also conditional correlation, conditional dependence, conditional independence. So we can actually do better than that. And these automap other methods require other inputs such as expert opinion. So they don't do as well without them. Although their runtime is good, right? But they don't do as well in terms of accuracy. So so my laptop will die. I don't know if I should stop or should I let it die? How should I proceed? If there are questions on Zoom, that might be difficult if I.
Well, that we can use my laptop.
Okay, so I'll continue then. Okay, so the SockShop application is one case study that we run. So this is like a pretend website where you go to shop for socks, right? And we can essentially use something called stress-ng tool to mimic an intervention on this system. And then you can test your algorithms and compare with the existing work, which is what this table is about. And then finally, we also run this on some real data that I'm not going to explain what it is, but there are 3 altitudes that we could obtain from real data. And we compared with epsilon diagnosis, and our method performs much better in the sense that it points to the right service. Maybe not exactly the right metric, but the right service most of the time. Compared to that worked. Thank you. Thank you. Epsilon diagnosis, although it runs fast, it cannot really pinpoint the right service or even right metric or even the right service. Okay, so very good timing. I'm actually done. So these are the publications to this talk. And if you have any more questions, I'll be ready to answer them. Thank you all for coming. And yeah, thanks.
Second that we have, is it true that this is or not, or would it be?
Yeah, so again, I think I skipped over, but the extension of the causal discovery paper I presented at the beginning to unknown targets that can handle any interventions target, any subset, any size, and even with latents, right? So we are simply taking inspiration from that, using it in a special manner. So it will be able to also handle multiple causes. We actually have the results in the camera already, but I didn't put them in the slide. So yes, it also works with multiple causes.
Any other questions? From the room? No questions. Let's end the speaker again.
All right, thank you.
Thank you. And next week we have our next.